that you end up with, and so it can go straight through the prism or whatever else you're doing. The other thing I wanted to make note of, and I'm going to do it in another lecture, I'll give you a hint, but you can't change the wavelengths of the various colors and think you're going to end up with a different light. In other words, blue light is blue light, the photons are blue, red light is red, the photons are red, and you can't change them. It's just part of the physics of the universe. So changing wavelengths doesn't really affect the color, as far as I know. Others can look at it and see, experiment with it. I don't have the means to do that, so that's just something else we can look at. All right, so now we know de Broglie wavelength. We can get a number for the kilograms. What does this mean? Let me change screens again. So what would happen if we had a mass? It can be anything. Not the sun, because that'd interfere, but right, and you have a light ray from a distant star. We already know that even with Newton's flat space, that a light would bend within the boundary of a mass, right? A gravitational sort of deflection. So this is the Newton deflection. Theta equals 2 times g times m divided by r c squared, which everybody knows is what it is. And so if you want to get Einstein's, you just multiply it by 2 and you end up with 4. So that's the gravitational constant, mass. R is radius. So you have light bending in a mass. Now, we know that. I mean, Einstein didn't come up with the idea that light bends with a mass. He came up with a different idea about curved space and time, but not, obviously, if Newton knew about it and light can bend, then you don't need the general theory in order to show that light will bend. It might be different slightly, but it still bends. So light rays bend in Newton physics. Gravity without need for curved space, so there's gravity there. Well, what does that mean? Right? The only way that you're going to get gravity as we know it is from a mass. This is back to Newton's version or view, right? In order to get a gravitational field, you have to have a mass. And although you say that a photon isn't much, but at least it's something. And the problem is that if you say a photon doesn't have mass, then Newton's third law of motion, which is basically opposite and equal, is breached. In other words, because if you're saying that a photon doesn't have mass, it's basically one way. A major object exerts a gravitational force upon the light, but the light doesn't do anything in return. There's a problem there. I mean, then the whole basis of physics starts to fall apart, right? I mean, if you're saying that a photon is massless in Newton's classical view of a gravitational field, it all falls apart. So that's the problem, right? If both phenomena, massive object and light quanta, do not have mass, then Newton's third law will be breached, right? You're saying it's not equal and opposite, it's just a one-way street. Yeah, that makes no sense. You can't use that. And you can't throw in general theory here, right? Curved space-time, because it's already known light bends in rays. So basically, the idea that you have a massless photon isn't going to work. So, right, so therefore, what's the upshot? What's the punchline of all of this? Photons have mass. They have to. There's no other way the universe would work without it. They have to have mass. So, what else? everyone knows, or everyone science should know, that there was an expedition in 1919. Arthur Eddington of the Royal Astronomical Society, I believe, and there were two groups, and they were looking at starlight behind a solar eclipse. And they took some pictures, they did took them home, did some calculations and whatever they did, and came up with the idea that, well, it's true that light bends in a large mass, and Einstein predicted what the number will be, and it fits. It wasn't that simple. If you think people were jumping up and down for joy and applauding and yay, no. It was very more circumspect than that. So that's for another time. So a photon has to have mass, at least in Newton's version of gravity, and it can't you can't use the general theory and just pretend, okay, now we'll make it massless. You can't use a mass with a photon in classical mechanics and then just throw it out so that Einstein's number will agree with it. It doesn't work that way, right? The photon's going to be in Newton's work. It's going to have to be in Einstein's work as well. And one other thing is it has to be in the standard model of particle physics, which is based on what? A massless photon. Well, I think a lot of this stuff is going to have to be reconfigured. You know, you have to put in a mass of a photon and reconfigure everything because it's wrong. It's simply wrong. Getting back to Eddington, he wrote a little poem. He wrote a little poem at the end of a paper about when he was presenting it to the Royal Astronomical Society. And in that paper, he wrote that light has weight, right? So what is he saying? Well, weight is equal to mass times gravity, and if you just Wg equals mass. So what he's saying here is light has mass. This is Eddington that was part of that expedition. So anyway, that's kind of what the work is. So what do I want you to take away from this? Again, a photon has mass, and it has a unique color in the visible light spectrum. It has a unique color and a unique mass that can't be changed. And we have to incorporate that mass into reality, not only with the Newton's view of the universe, but also Einstein's, and also particle physics and any other thing. That it's going to, I think there's a lot of work in there for people that are looking for a doctoral thesis or a master's thesis or something. So anyway, that's what I have. And again, you can reach me at blumdahl300@gmail.com. And I look forward to your comments and questions. Thank you.